revision video, somebody asked me specifically about the extraction of bromine. Now, that kind of involves redox chemistry, but a little bit of Le Chatelier's principle. So the basis of it is using chlorine to oxidize the bromine from bromide to bromine. Although it's a little bit more in and out than that, as we will see. And there's also the use of sulfur dioxide with bromine, which is again some redox chemistry. So there's two lots of redox chemistry. We need to be able to do oxidation numbers, which I'm not going to cover in this video, but if somebody wants that, I suppose I could do one. And there's also a bit of Le Chatelier's principle in one of the stages, because it's an equilibrium and you use the conditions to maximise the conversion of bromide into bromine. But we'll cover all of that as we go through the stages. There are 4 basic stages within the extraction of bromine, and these things appear within it. So I need to prep the board for stage 1. I'll see you after the edit. So stage 1, I've got 3 parts to it. The first thing is that you have the source from the natural environment which contains bromide ions. Much mention of the Dead Sea in the, down in on the borders of Israel, and if only my geography were better, which is a highly saline environment. It's the lowest point on Earth and all the salts concentrate in there. And then you can also find that people extract it from seawater as well, because the level of bromide in seawater is, well, not massive, but it's noticeable enough that you can extract the bromine from it. So that's one of the Irish chemical industries apparently. So first thing you do is you set the pH of the whatever source of bromide, and it's always dissolved already, it's aqueous already, and you set the pH to around about 3.5 using sulfuric acid. Now the reason for that is this equilibrium here, where bromide ions in acidified conditions, which of course HBr, when you are talking dissolved, so these are aqueous, so bromide ions will split up into H plus and Br minus. You also would have H plus and BrO minus bromate 1 ions. Bromate 1, because the oxidation number of the bromine in that compound is +1, so it's bromate 1. And that exists in an equilibrium with bromine itself. And in the process it forms water. Now, by raising the level of H plus ions using sulfuric acid, it puts lots of extra H plus ions in, so that drives the equilibrium back over to the bromine side. So what happens is that when you acidify it, the source of bromide, seawater or whatever, goes orange because of the bromine. Only faintly orange, I would imagine, because the level of bromine is quite low when you do this. But the first thing you do is you use Le Chatelier's principle to push bromine production. However, that will still leave lots of bromide ions. So you've formed some of the bromine that you need, but there's an awful lot still as bromine and bromide ions. So what you then do is you add chlorine, and adding chlorine reacts with bromide ions. Standard bit of laboratory chemistry. You do that displacement reaction between all the halogens and the halides, and you use a bit of I usually use cyclohexane to pick up the colour. And so here you would again convert more bromide into bromine, which would then be orange. So stage 1, drop the pH to 3.5, because seawater and stuff is quite close to neutral. Use the H plus because it forms some of the bromine, and then use chlorine to form more of the bromine. It will also undo the BrO minus ion as well, and that ends up back as bromine. So It's impure at this point. There's lots of other things floating around in there, and you need to go through a process to extract the bromine from all the other stuff and then get it to be significantly purer than it is right now, like 100% would be ideal. And that's where the next 3 stages come in. So we're going to have a little break whilst I get the board ready, and I'll see you shortly. So stage 2, going to get the bromine out of that mess that it's in from stage 1. Fairly straightforward, just blow some air through it. Blowing the air through it vaporises the bromine out of the solution. Bromine's not particularly good at dissolving in water, certainly as Br2. So it leaves, it ends up mixed with the air as a vapour, so there's bromine distributed in air, but it also will pick up some of the residual chlorine and some of the hot water that's there. And so you end up with a kind of a whole load of things carried in air. And the next thing is to take this impure mixture of bromine and air and start to work with that. So that we need to get the board ready for stage 3, because stage 2 is literally just blow some air through, get it all vaporised. And we'll go on to stage 3. See you in a moment. So when we get to stage 3, we reconvert bromine back into the -1 oxidation state. Seems rather odd, but it's all part of the purification of it. So the bromine coming out of that air, that wet air bromine, it goes into, I presume, a big vessel, and they put sulfur dioxide gas in there with it. And this is the reaction that takes place. Now this is a redox reaction. If you look at the oxidation numbers, bromine there is 0, bromine there is -1, sulfur there is +4, and it ends up in the sulfuric acid, which is +6. So when you look at that there has gone down. He lied. It's gone up by 2. Down. Ooh, that's not right. So it's gone up by 2, and then the bromine has gone down by -1. It's gone from 0 to -1, but there are 2 bromines, because Br2 means there has to be 2 bromines going down there, and that's a drop of -2. That's an increase of +2, and therefore oxidation numbers are balanced. The rest of it is just put some water in to get you the oxygens to produce the sulfuric acid, because you need 2 extra oxygens, and then you need the 4 hydrogens for that. That there represents the fact that you have increased the concentration of, and now we're at bromide by the time we finish this, the concentration of bromide is now 2,000 times the concentration you started with in stage 1, when you started with the natural starting material that had the bromide ions in. So that's a significant gain in terms of concentration. You can write that out as ionic, same 3 things, put the 2 in, same 3 things there, because none of those will be ionic. That's a molecule, that's a molecule, water is a molecule. However, HBr splits up in aqueous solution, and because there's lots of water around, it becomes a concentrated, or relatively concentrated solution of HBr. But in solution, that will split up. That'll give you 2 of the hydrogens. Sulfuric acid gives you another 2 hydrogens. Although there's things about sulfuric acid and the way it splits up. But we're saying it does. And sulfate ion, so that makes 4 hydrogen ions. And there's the ionic equation. At this point, we end up with hydrogen bromide in solution, and we're 2,000 times gained in terms of concentration. But then we need to get back to, because obviously this is about the extraction of bromine from seawater, so this is obviously not bromine. Stage 4 is then get it to be bromine again. I'll see you ready for stage 4. See you in a moment. So the final stage, oxidation of HBr the result of that oxidation will be the bromine that we're looking for. So coming out of stage 3, you have that HBr solution. So what you do is you convert the HBr into bromine. You do that by blowing steam, which will raise the temperature, and chlorine in that steam through the HBr solution coming out of stage 3. So that gets heated up. The bromine produced, which is this reaction here, chlorine plus the 2 of the HBr which are in solution, which I haven't put on. So chlorine reacts with the 2 HBr, makes hydrochloric acid in solution and the bromine. But because of the steam, it comes out as bromine gas. It's lifted out of that solution into the vapour phase again. That is a redox reaction. Chlorine is 0. Chlorine is 0, chlorine there is -1. But it's 2 chlorines, so that's a drop of -2. The bromine sits at -1 in HBr, it becomes 0 there, and of course it's that's an increase of +1 times 2 plus 2, which is what you need to have in a redox reaction. You need as much reduction as you do oxidation in terms of oxidation number totals. There it is as an ionic equation where the H+, because the H+ doesn't do anything, it just sits there in solution as a spectator. So there's the same redox reaction with the chlorine and bromide becoming chloride and bromine. This is in the gas phase, so you cool it and you get liquid bromine, but it comes out wet. So you get liquid bromine with some water in there as well. So what they do is they dry it using concentrated sulfuric acid. Now there are a number of drying agents out there, but concentrated sulfuric acid, which perhaps not thought of as a drying agent, certainly GCSE, you don't ever think of it as that kind of thing. It will pull water out of things quite successfully when it's concentrated until it gets to a slightly lower concentration and it stops doing it. So it will dry the liquefied, so you condense it, the bromine becomes liquid because bromine is a liquid at room temperatures, standard sort of temperatures, but it's wet bromine, and then you dry it with conch-sulfuric, and there's the bromine that you're trying to produce and trying to sell. There is a waste stream from doing this, which is the sort of process, let's say it was seawater or Dead Sea water. It's acidic because of the sulfuric that went in with stage 1. People don't seem to worry about that. A little bit concerning, but there are traces of bromine and traces of chlorine in that waste stream, and it's treated with further sulfur dioxide. That's the reaction that we had earlier in one of the stages. So that same reaction with the sulfur dioxide converts those into, because these are particularly bad for the environment. I mean, bromide ions and chloride ions are natural to the environment at lowish, actually not chloride, chloride's quite high in the sea. But using sulfur dioxide you convert those into halide ions and then they go out to sea. Some people would say, oh, should we be polluting the ocean? Well, you can't really pollute the ocean with chloride and you can't pollute it with bromide because, well, they're there anyway, you know, it's a natural thing. The only issue, I think, personally speaking, is that the acidification, because acidification of the oceans is a massive issue due to the carbon dioxide dissolving in the ocean and acidifying it and causing issues with coral reefs and so on, with, you know, the dissolving of the limestone. But there's the process finishing with liquefied bromine. After it is dried, it is then ready to be sold on. Now I was asked quite specifically, how does that work, because the person's read it in their textbook and went, I can't quite understand that. They maybe didn't use their hands. And there's the 4 stages set out a little bit more clearly, hopefully. Thank you very much. That's kind of it. We'll come back with another video about some other revision topic that I've been asked to do very soon. Thank you for watching. Buy the book or books. See you soon. Bye.